In this lecture, what we're going to do is we're going to take a look at properties of pure substances, and we had talked about property data last time. We will be going through the different tables and diagrams that we will use, typically found in the back of any thermodynamics textbook. So what I'll be doing is walking you through a couple of the tables, or a number of them, that pertain mainly to systems involving steam, and those are commonly referred to as being the steam tables. And then the other set of tables that we'll talk about are tables involving R134A, a refrigerant. So to begin with, what we're going to do is we're going to take a look at properties of pure substances. So when you're solving problems in thermodynamics, you're looking up things like specific volume, enthalpy, entropy, internal energy. Those are all the different things that we need in order to solve the problems that we're going to be working with. And so consequently, knowledge of how to read these tables or diagrams and how to deal with them is quite critical to progressing through mechanical engineering thermodynamics. And typically when we're looking at these properties, they will be presented as a function of pressure and temperature, and the things that we're pulling out are things like specific volume, internal energy, enthalpy, and entropy. So if you recall back when we talked about the first law, we were talking about being able to characterize the amount of heat or work going into a system and the change of energy. Well, these properties are used for doing those energy balance calculations. So in this lecture, what we're going to do is we're going to take a look at the methods, and they will present the tables themselves, that you'll be using throughout the course. So we're looking at properties for gases, liquids, as well as two-phase systems. So those would be systems whereby a liquid is going through a phase change to a vapor. So it's basically going through the boiling process, and we'll talk a little bit more about that later on. So in doing this analysis and extracting out these values, we're going to be relying on both tabular as well as graphical presentations. So we're going to be looking at tabular data, so basically reading tables, and we'll also be looking at graphical or charts. I personally prefer using the tabular because when you're using the graphical, although you perhaps could do your calculations quicker, it's more prone to error because you have to read values off of the graph, whereas with the table, you're doing a lot of interpolation, but nonetheless you can get more accurate results that way. So first of all, we're talking here about pure substances. We're not talking about mixtures or gas mixtures like you would have with combustion, which we will look at later on in the course. So we're looking at pure substances. And what that means is that we have fixed chemical composition throughout. When we look at combustion later on in the course, there you have chemical reactions, and so the composition is changing due to the chemical reaction. But we are going to assume that we're looking at pure substances. Another term that we will use, and I've already alluded to it when I said two-phase system, we're looking at phases. And if you recall from a course perhaps in freshman physics or something like that, the phases that we can deal with, we have a solid phase. And when you have a solid phase, the molecules are arranged in a three-dimensional lattice pattern. And consequently, the molecules are not free to move around. Through the application of heat, the solid goes through a phase change process and changes into a liquid. And we will be looking at properties for liquids. The best way to describe a liquid is you have the molecules that were in the solid, they then kind of become free to move in what we could unscientifically call chunks. So chunks of molecules so they're still in the lattice pattern, but the chunks are free to float about. And finally, what will happen is as you apply more heat, we eventually get into the gas phase. When we're looking at steam tables, sometimes we refer to that as the superheated or the vapor phase. But in this phase, the molecules are far apart. They're far apart from one another and they're free to move about and collide. And we'll talk a little bit more about the different stages of gas or vapor at the end of today's class. So with that, let's just take a quick look at the phase change process itself. We've all witnessed water boiling in a pot on the stove. And essentially what that is, that's going from liquid to vapor or through a phase change process at atmospheric pressure, whatever the local atmospheric pressure may be. So if we plot temperature, here we'll put it in degrees Celsius, and then let's say we put specific volume on the horizontal axis. What will happen as we're heating the liquid, so let's say it's water, we're in this range here and we're increasing the temperature, and eventually we get to a point that we refer to as being the saturation temperature. So this is a line that's at a constant pressure is what I've drawn here coming up to the saturation temperature. So what happens is we increase temperature, then we get to a point where we hit the saturation point, and that's when we're going through the phase change of boiling, and we refer to that as being a saturated mixture. previous to that, before you even get to the saturation point, we're in what is called the compressed liquid region. So that's compressed liquid. We get to the saturation point, or basically the boiling point at the particular pressure that we're operating at. We go through a phase change, and that's the boiling process. And during going through that phase change, we have a mixture of both liquid as well as vapor within the system. And then we go up into the superheated vapor region, where you no longer have a liquid, all you have is vapor. And this line, the solid line here, is for a constant pressure process. So we're assuming that things are at a constant pressure there. And there are a couple of points to denote here. First of all, the one going from compressed liquid to saturated mixture, that is where we have what is referred to as being a saturated liquid. And another point to denote here, on the right-hand side of the two-phase region, is referred to as being a saturated vapor. So you can see in the video on the right, what is happening is we have a vessel. It's basically a kettle. And when we're below in the compressed liquid region, if this is our container, we have liquid in here. We have convective currents going as we're heating in the kettle, but there's really no boiling going on. We just have liquid. So that is liquid phase. Then what happens is we start going into where we have nucleate boiling. If you take a course in heat transfer, you'll learn all about the boiling processes. But basically we have bubbles that start to form on the bottom of the kettle, and they slowly start to move up in small columns and things like that. You have localized boiling at the bottom, but for the most part the liquid temperature is still below the saturation temperature. And then eventually what will happen is you get where the upper interface is hard to see because we have all the bubbles in there. That is where we have a two-phase mixture of both a liquid and a vapor phase. So to draw arrows back to our diagram here, this would correspond to this region. In the middle here, that would correspond to getting close to the saturated liquid point. And then finally in the video, this here would correspond to in the middle where we have a saturated mixture and we have boiling underway. So that's where we have a mixture of both a liquid as well as a vapor.